let's begin. So I'm going to be showing you an example illustrating a type of modeling. What I really want to show off in this example is how to do Gibbs sampling. Show that the problem's slightly complicated and we wouldn't know how to do it back in the late 80s, but along comes the early 90s and we now know how to solve this problem. So the example that I'm going to be showing you comes from this paper right here. So this is one of Gelfand and Smith's original papers on this. I always cite Gelfand and Smith 1990, which is a JASA paper, but this is where it all happened first. And you can see the date on this. You know, in 1989, and just looking at this, you can kind of see that this was typed. So this was a long time ago. But what I'm going to be showing you is a model that they eventually get to. Show some math, show how to work out some stuff. Their notation is going to be slightly different than what I use in class. These are inverse gammas, so they're modeling variances instead of precisions, where we model them with gammas. There's a data set in here. Let's see if we can just scroll down. Here is the data. So this really is a pretty old paper. And so here's the data, and the data corresponds to rats' weights over time. Okay, so what we're going to be doing is we're going to be looking at, I'll call it W, T, and I'll say I, is going to be equal to rat weight at time T. And I'll say this is going to be the ith rats weight at time T. And so this is what that data set is. So Gelfand and Smith, 1989, somebody came to them and said, I have this really cool data set. And so you can even tabulate it in a paper. So those days are gone. We don't do anything like this anymore. Science kind of just looks different. They wrote about 6 papers on this same exact topic. And they all kind of look like this. But if you are citing a paper on this, I would go to the JASA paper, 1990. So they want to model these rats' weights over time, and they know that there's certain correlations going on within each rat. Obviously, a rat's weight through time is associated with how much they weighed last time. So we're going to write down exactly the same model that Gelfand and Smith used. And this model is right here. So this is everything you need to know. And so it's kind of funny that a lot of papers, they say a lot of stuff. And everything you need to know is usually contained in very small sections. And so, but this is the whole model, and I want to discuss this. So we ended up writing it down a little bit different. I'm going to use W's instead of Y's, and I'm going to use T instead of X for time, but we'll keep some of the same notation. I also want to point you in the direction of a supplementary handout on precision matrices and what the meaning of zeros within precision matrices represent. And so if you need an English verbiage of what the zeros in precision matrices represent, here it is. So they show conditional independent structure. You have to condition on everything else out there. And so that's a very important technical detail. So you can read through this if your normal theory is rusty. So basically this is regression 101. Okay. That's it for the computer. Let's get on with modeling these W's. Okay, so we want to model this. So our goal is to model the WTIs. Okay, so I'm just going to start writing down a model. Now, the model I'm about to write down you probably wouldn't use anymore. It's a little bit too simple. It's not a real time series model, but you know, you might go for like moving average models or autoregressive models or ARMA models if you put them all together, and maybe that's a better model than what we're going to write down, but we can quibble over modeling details later. I think this model does have some merit. So here's the model. And this is from Gelfand and Smith. So WIT is going to be equal to alpha, and I'm going to change this in just a moment, plus beta t plus air t. This is time. So that's our covariate right here. So this is an intercept, and this is a slope parameter showing us how rats accumulate weight through time. And so if beta was very big, it would tell us that rats were putting on a lot of weight through time. If beta was very negative in big, it would say through time they're losing a lot of weight. That would be our interpretation. So one extra bit to this is we want to let each rat have its own corresponding parameters. So these are rat specific parameters. So every rat has its own set of an alpha and a beta, an intercept and a slope, and they represent that rat's ability to put on weight through time. And so there's also a little bit more. We want to model these as random. Want to let these be random. So let alpha I, beta I be random. So here's the idea. Every rat was bestowed an intercept and a slope parameter upon birth. And those intercepts and slopes have all the information encoding their genome with respect to putting on weight. And so there was some population, we grab these parameters, alpha and beta for each rat, they get them, and they're stuck with them through time. So this is the idea. So we want to model this as random. So alpha I, beta I, I'm going to give this just a little bit of notation. This is going to be theta I. So this is just a vector. This is going to come from a normal distribution. Also, these errors right here are going to be normally distributed. So we can start making some simplifying assumptions. Maybe the variability of each time series is the same for all rats. Now, I'd probably change that. If I were just looking at it, I would think maybe there's not a global variance right here. And so, but we'll just let it be sigma squared. That's what they used in the paper. You could maybe throw an I down on there if you thought rats varied a little bit different. And I probably would guess that they do. And so this is a fixed effect over all rats. And then I have to model this somehow. And so we might say it's got some mean. Right here, I'll call this theta naught. This is just alpha naught, theta naught. And so this is the population average. So in the whole population of all rats, there is an average tendency to put on and accumulate weight. So that's the idea here. And so we want to learn that parameter as well. And we might have a question that maybe these two parameters right here are associated with each other. So let me just ask you a question about it. Do you think alpha for a rat, a particular rat, should it affect its propensity to put on weight? Should alpha affect beta?
Probably. So rats with a smaller bone structure might have harder time putting on weight.
Yeah. So maybe so. And so what is this right here? How do we interpret this? If I think about at the first time point in all of this, so when t is equal to 0, then this is the rat's weight when it comes into the study. That's how we might interpret that. So this is its weight on day 0. And so, should its weight on day 0 have some influence on the rat's ability to put on weight? And I think the answer is probably yes. So if you're bigger, you probably put on weight faster, maybe. So could go the opposite way. Could be you're bigger so you can take off weight. So I've seen people, we've all gone to the gym, and it's like we see some, skinny kid in the gym, and they're trying to put on weight, and it just is really difficult for them to do. But some big athletic person comes into the gym, and it's like they put on 40 pounds quick. And so something about your skeleton, something about how big you are probably has some influence on your ability to put on weight. Now we could argue all day about which direction it goes, but maybe we should just go get some data and measure it. But I think this thing right here should be dense. So this is a dense covariance matrix. So in the diagonal term, the correlation is going to tell us how associated these things are. And so this is always fun when you get a data set and you start thinking about, what are the mechanisms, the dependencies inside of the model. And what I usually say is build your very complicated model and try to measure everything you can. If you so found out that there were negligible effects, if you did your estimation and you found out maybe the correlation was really close to 0, maybe I would pull it out of the model. Why might I do that? Because I can leverage my data a little bit more. And so I'll have better power. If I start including a lot of parameters into my model, it's going to bring down my power, increase all my variability and everything. I have to use that data to estimate too much. But we're going to start with this and see if we can learn what that correlation parameter is. Now, all the answers to this are in this paper. So they inferred everything that I've written down on the board. But what I want to point out is these are random for each rat, and this is fixed right here. This is called a mixed effects model. So let me just give you some language. Random effects. Plus fixed effects. And the language is that random effects vary randomly for some subgroup of the data. So let me give you another example, just to branch out a little bit. Imagine we were in a Stat 101 class, and this was a big auditorium class at Virginia Tech. And there's a whole bunch of these classes that go on all the time. And we want to be able to compare these classes directly to each other. And so scores in one class should be representative of scores that you might get in another class. But it's a little bit random. And so some of the random impacts might be who your teacher is, or what time of day you take that class. And so there's all kinds of random stuff that goes on. And so maybe your teacher effect, maybe there's 5 instructors that teach these big auditorium classes, and everybody's like, I want to go to instructor A because this instructor teaches better. So they might say, I want to go to instructor B because that instructor gives very easy, grades very easily. So that's usually what ends up happening. But this is just a statement about the way that I understand the universe. There's some baseline average, and each rat is a random draw from this. And it kind of makes sense. Like, if you study genomics, this is about what happens. It's just that we don't get alpha and beta per se, we get genes, and it's a random selection. So this is our whole model. I haven't said anything Bayesian about anything, but it sure does look Bayesian. And so you will, if you get into a room with half Bayesians and half classicists, and they start talking about random effects models, there's usually a lot of confusion. And so people start asking things like, is this a prior? Sure looks and feels like a prior. It's a mechanism in the data. I could have explained this all very differently and just said, these alpha and betas, they just vary between each rat. I want to let each rat have its own individual parameters, and I can throw a prior on that. Or I could say, I want to think about, as a model, this random behavior in the alphas and the betas, and I want to model that. Classicists will do this as well. And so what they'll typically do is they'll do something like maximum likelihood estimate for this, but they will get a distribution on alpha I and beta I. And it creates more variability in the system. I don't really care how you think about this, but just know that the terminology is a little bit different. You'll see non-Bayesians write this stuff down and they'll say it's a random effect. You'll see Bayesians write this stuff down and they'll say that's a random effect. And sometimes you'll see Bayesians come and say, no, there's my model, that's a prior. And so mechanistically, what you end up doing at the end of the day is exactly the same thing. So Bayesians that operate with random effects don't change any of their operating procedure. They go about business just like a Bayesian normally does. Classicist, however, does two different things for the random effect and the fixed effects. They'll estimate it differently. For a Bayesian, we operate exactly the same. So hopefully that's not too confusing. It really is just kind of a language sort of thing. I kind of like to write down, here's my model. And once I put down my priors, I say that's part of my model as well. So at the end of the day, I just have model, and everything in my model can be estimated through Bayesian inference.
So for our purposes, what are we calling a random effect and what are we calling a fixed effect?
So what we'll do, just for the language, this is a random effect. This is the only one. And then these things, these variances right here are fixed for each rat. And these are global population parameters. We want to estimate those as well. And so how will Bayesian do it? Bayesian's just going to put a prior on everything they don't know. We don't need a prior on this, however, because it's already random in the model. So let's just finish this up. So to complete a Bayesian inference, we need some priors. What do you need priors on? Anything you're planning on estimating that already isn't random. And so I need a prior here, I need a prior here, and I need a prior there. So let's just write this down. Pi, theta naught. Let's write down sigma inverse. I like modeling the precision. Why? Because I like dealing with sharp distributions instead of the inverse version of them. And we need pi sigma squared. We can leave it like that. So what would you guys pick for this? We can probably guess what Gelfand picked. What's that? Flat. Yeah, flat sounds pretty good. So what do you think? Anything else? So they ended up doing the full-blown conjugate analysis. They put a normal in here. And so they'll have a hyperparameter mean, and they might have some hyperparameter controlling the variance. What Melissa's saying is take that variance and increase it up to infinity. And so I would probably use this as well. Pi theta naught proportional to 1. So this is the limiting version of it. And so what are these parameters? They're shift parameters. So what would you pick for this? Bless you. It's not a trick question. Wishart, yeah. It's always the backwards one. So it is, on the inverse scale, it's Wishart. On the non-inverse scale, it's inverse Wishart is what you would pick. Wishart. So how would I parameterize it? I guess I have some choices. And so here's what Gelfand says to do. Build in some parameter right there, and he tells you how he selects it. And then he ends up putting in some covariance matrix, right here, R, and divides by rho again. And so what happens right here? Expectation a priori on sigma inverse. This is just going to be R. So what do they pick for R? They pick the identity. So they wanted to say a priori, I don't think they're correlated. The data's got to tell me that. And so possibly let this be the identity. So your prior is not controlling the off-diagonal terms, your data is. And so your data is going to say whether or not these are associated and how associated are they. Just to wrap this up, what would you pick here? What's that?
Yeah.
Maybe. This one would be the inverse gamma,
Right.
because I put it on the variance scale. So, would be inverse gamma, maybe. I would probably pick this. This is equivalent to 1 over phi as well. You can do the transformation, 1 over that scale parameter. And so, how do I go about business? At the end of the day, you give sample using all of this. Complete everything. We need to find our full conditionals. Posterior full conditional, this is everything else. It's really annoying writing this over and over and over again, but really everything else is the data. Theta naught, all of these other parameters. I've got a whole vector of these theta i's. Theta I goes from 1 to t. However many time points we have, it has sigma squared in here, and that's it. So instead of writing down everything else all the time, usually people just write a bar right here. Need to figure these out. Theta naught, given everything else. I need my theta i's, given everything else. This is my random effect. It's already random in the model. I didn't need a prior to go on. And we need to figure out pi sigma squared, given everything else. Once we do all of that, all we have to do is run those things in a loop. Over and over and over again. So I posterior update this parameter. I draw from a Wishart distribution. I plug that thing in. Then I draw from some normal distribution. Then I plug all that stuff in down here, and I draw from a whole bunch of normal distributions. So there's going to be I goes from 1 to however many time points there are. So I'm going to run those in a loop, draw all of those, and then I'll update sigma squared. And I'll do it over and over again until this thing converges and gives me a whole bunch of samples from some stationary distribution. At the end of the day, I've got this big joint posterior sampler. And so, and it'll tell me how all these parameters in this model are related to each other. So maybe they have strong dependence on each other, maybe they're weakly dependent on each other. The data will tell us. And so in order to do this, the hardest part of this is writing down the likelihood function. And so every year when I give this as a problem, people come in and they're like, if you could just write down the likelihood for me, I could do this problem. And so hopefully we can start getting into how we write down our likelihoods. So what I think I'll do with the remaining time here is write down the likelihood function for you guys. And in return, I'm going to ask you to actually run the Gibbs sampler and do draws from this until it converges. I'll take that data set and encode it as a text data set for you, and I'll send it out so we are not all doing it. And so I'll just hand encode it because I don't know where the data set is. I'll put it on the website, and you're going to take this problem all the way home by working out all of the full conditionals and implementing everything. JB?
For the set of theta i's, it should be I equals 1 to n, or however many rats there are.
Oh,
We're not
you're right.
crazy good.
Number of rats, absolutely. Yeah, these are all rat-specific parameters.
And also, everything else beneath it, that's the I 0 to N, right?
Yeah, number of rats. Absolutely. Okay, so let's get some notation down. Actually, let's leave this up here. So notation. Let's just let there be n total rats and t total time points. This is a really convenient data set because we have each rat staying in the model throughout time. Things get interesting when maybe a rat dies in the middle of your study or something like that. And how you treat that has to be done statistically. And so that's called data censoring. We don't have any of it here, but if you want to know about all that stuff, take a survival analysis class. That's what they teach in survival. Okay, so our likelihood. We've got a whole bunch of parameters in here. Theta naught, theta I goes from 1 to n. Sigma squared, and I think that's it. Given all of our data. So I'll do the easy part, up to proportionality. So here's how I always write down my likelihood. I look back at the model and I think about what happens. And so each rat has a time series of data. How is that time series generated? First, I draw one of these for the rat. Each rat gets exactly one of those, and then I generate the whole time series. So given those things right here, then I can generate the whole time series. So let's just write that down. I goes from, I'll say, let's go T, goes from 1 to cap T. So this is going to be for each rat. They're going to have a time series. And I need to write down what happens stochastically here. So this is going to look like this. I've got a normal distribution. We can write in our 2 pi's. I've got my variance parameter. It goes right here. E to the minus 1/2. I know that this thing is normal, so I'm using a normal innovation. This is going to look like sigma squared. Then I've got W, I, T, minus my regression log. And I need a little bit of notation to write all that down. And so we could write that as alpha I plus beta I T That's what I could put right there. Or I could start building some notation and start working in linear algebraic form. So I've already got some notation for this. And so I'm going to say this is going to be theta I times 1t. So I read that exactly the same. So this right here is alpha I, beta I, and I'm taking an inner product with 1t. So exactly the same thing. And so I would write that down like that. It'll make everything a little bit easier at the end of the day. So this is going to look like 1t theta I. And I need to account for the random variation of rat I. So I need to write down p theta I right here as well. So this is just going to look like, we can get rid of our 2 pi's, if you will. This is going to look like sigma. I'm looking at this part of the model. And I'm just going to write down its PDF for that step of the model. So this is just going to look like sigma inverse to the 1/2 e to the minus 1/2 theta I minus theta naught transpose sigma inverse theta I minus theta naught. And now I need to product this up over each I. Each rat. 1 to n. And there it is. So, piece of cake. So again, what this says is I draw from this for each rat. I plug those parameters in here, and then I get my vector of time series. And so be very careful with what you're producting together, where the products start and stop. So this is probably the hardest part of this problem, is knowing that this right here, this product doesn't extend over this stuff. So each rat has one random draw. It doesn't happen throughout time. And so writing down these full conditionals gets really easy once you've seen this. So once you write down the likelihood function, now I can just think about what the full conditionals are. If I want to get this full conditional, I just have to look at parts where sigma inverse appears in the model. Sigma inverse doesn't appear in any of this, right here. So for this posterior update, this whole interior thing is part of the normalizing constant, and it just falls through. And so all I'm left with is this product right here over all of the associated rat vectors. So let's just write it down. Pi sigma inverse, given everything else, is going to be proportional to pi I goes from 1 to n, sigma inverse 1/2 e to the minus 1/2 theta I minus theta naught transpose sigma inverse theta I minus theta naught times our prior. So if you look at this right here, this is going to be a Wishart, and this has the same form of being a Wishart. I need to take my trace after I pull this through, drop it in through the sum, and then I need to take a trace and do that cyclic permutation, and I can figure out exactly which Wishart this is. So the mechanics of that look exactly like what I did last time when I worked through a posterior distribution on sigma inverse. And so that's it. So then I need to figure out how I update these parameters. I look at my entire likelihood and I think about where theta naught shows up. And I'm in luck. Theta naught only shows up again in this part of the model. So I would be using this same part of the likelihood. Multiply by my normal prior or my flat prior. I like that choice. And I've got my full conditional. I want to update the theta i's right here, and I need to run through all of them. So through the number of rats, which is n. This is going to be a normal distribution as well. Where do I find those parameters? Well, that's a little bit more interesting because the theta i's show up in this part of everything as well as this part. But most of the theta i's don't matter in it. Most of them fall out. So for theta I, for each theta I, this thing only shows up one time in the likelihood. And this part only shows up one time as well.
So for the product from I is equal to 1 to the n, we only took the first part, and for the second part, which is P of theta I, it's not taken under the product, right?
Yeah, there's only going to be one of these in that product and one of these.
What do you mean by one of these? So is the product over, so the I in the index, does it correspond to the product or no?
Not this product.
The first one,
This one, yes.
Yeah.
That's what the I is referring to.
okay.
Yeah, so this is the hard part of the problem, is just
And
knowing
what
where
if
those
we have
braces
to do
are.
another product? This is what confused me here. So I understand why we did the first product for
The time series.
yeah.
Then I have all of my rats. So now I'm just producting it over each rat. So
And
this
you're
is
assuming
rat
that
i's time series. And now I'm just producting over all I rat,
And
all n
it's
rats.
only a condition if you
That's right. Everything is conditionally independent. It is hardly independent. Bless you. So the posterior update here is pretty easy, and then we just need to update sigma squared. Where sigma squared, it's not in this part of the model, and so sigma squared shows up here. So it's in both parts of the product. So you're going to have double product because it shows up n times t times. And so that's the name of the game. And so this is Bayes, I would say, 2006. So everybody was just writing down all their full conditionals. They'd derive them for you in a paper. Then they would run their MCMC and they'd show you your trace plots showing that everything converged. And nowadays, you're not allowed to do that. So people are tired of that. So you have to say something much more interesting. So, but if you read through Galpin and Smith's paper, that's precisely what they did. They just wrote down these full conditionals, and then they show you some trace plots. Any questions about this? So I'm going to ask you to do this on your next homework. So I'll just give you a heads up as to what the homework's going to be. It's going to be all the problems from homework 3 that you didn't touch. Those all include this Wishart thing. And you're going to be coding that. So deriving everything, encoding it, showing me trace plots, giving me a little bit of model output, and that'll be it. So you can get started on that if you have a lot of free time right now. Otherwise, I'm going to be here tonight at 6:30 and we'll do yes, no, maybes. So I'll write yes, maybe in the middle, no, and you can ask me what's going to be on the exam and I'll put it in one of the columns.
So from my understanding, like in econometrics, we usually refer to the random effect, or both the random effect and the fixed effect as the error components. It's
Yeah.
like the alpha I, gamma I, or beta. So here I'm a little confused that is this the same notation here, or
It is. It's just the fixed effects I put priors on.
okay? So you mean that for the sigma, it's the fixed effect in the econometric model, right?
And then I also put priors on this as well. So what do you want to call those? Well, if you called it a prior, you would have said those are hyperparameters. But they're not really, because I'm about to put a prior on it. So this is really a hierarchical model, you might say. So I kind of like to just call this a hierarchical model. I don't love the language disputes when people show up and they're talking about random and fixed effects, because it doesn't matter to me. It's like, just write your model down on the board, and you call it what you call it, I'll call it what I call it. but it sure has wasted a lot of time at a lot of conferences. So what we actually call these things. So you'll have your language, I'll have mine, but I'll stick with that's the random effect. Sigma squared is a fixed effect.
So I just want to clear, we are talking about same thing.
Yeah, I think so. Pretty sure. Any other questions? That's it. I think we'll end a little bit early.